Jacob Eapen, thank you so much for everything that you've done, for getting me out here, showing me around, taking me out. This has been a blast of a trip, and it's all thanks to you. Thank you so much.
Thank you, Brett. It's my pleasure to have someone like you with a lot of passion and commitment to the next generation of nuclear plants in our country and in the whole world.
Yes.
So my great pleasure to have you here at NC State.
Yes, boy, I mean, over the last 5 hours of conversations, you and I have probably touched upon every worldly subject there is. But now we get a chance to talk about you and your background in nuclear. So tell me, how did it all begin for you?
So I graduated in India from University of Kerala in mechanical engineering. So that is something which I share with you.
Yeah.
And I was looking for a place where I can do research. So there were a few places in India at that time, space. So we had a space center in my hometown, and that was one of the things I was looking at. But then I also found that there is this nice opportunity in Bombay, now Mumbai, where there is research work done on nuclear reactors. So I'm a mechanical engineer, so I learned quite a bit on the things on gears and thermodynamics and fluid flow and all those things. Really love those material science, manufacturing, machine drawing, and all those things. So I was equipped with those kind of things, but I had absolutely no idea about nuclear. So the opportunity at Mumbai was great. I liked a little bit of physics. I always wanted to go in that direction, and that gave me a great place to start my career in. So I joined Bhabha Atomic Research Center.
And what was the opinion of nuclear in India at the time? And even today, how did you feel going into the space when you did? What was the perception?
So unlike in the U.S., it's looked at in a very positive manner. Those are like the shining stars of Indian economy, in the country as such. So space and nuclear, they are at the forefront of technology, and India to be in that particular club, it means a lot to a lot of people. So it is
very prestigious.
Very prestigious, yes. And nuclear and space would attract some of the best minds across the country. Yes.
So what were some of the things when you joined the Atomic Research Center there? What were some of the areas that you guys were investigating?
So again, I had absolutely nothing. I mean, I knew nothing about nuclear. So we had a training program which lasted 1 year, very intense. So we had 5 days of lectures and maybe some practical visits, training and things like that. And then on every Monday we would have a test for 3 hours. So very intense. And that covered pretty much, we had to know about nuclear reactors, from reactor physics to operations of reactors, chemistry, material science, electronics, tons of stuff. So very intense. And that was the platform on which when I started my career.
It's almost like a boot camp for nuclear.
It is a boot camp, yes.
Yeah.
Very intense. But it really prepared me to the world of nuclear. I really loved.
And then so where did you go from there after you had this training?
So there are several openings, we had openings in reactor safety, we had openings in reactor engineering, we had, there are tons of other places. I didn't know much about reactor safety, it just sounded nice. So that was one of the things that was available to me and I was interested in. So I joined a division called Division of Reactor Safety.
And this was safety of what type of reactors? Are they mostly CANDU?
CANDU type reactors. Yeah. A lot of modifications were done in India. So
what modifications? Yeah, how did the design change when India adopted it?
So not a lot when it comes to the basic reactor physics and even engineering-wise. But then there was an offshoot of the CANDU reactor that I worked briefly on. It was called the Advanced Heavy Water Reactor. I haven't followed what has happened since after I left Bhabha Atomic Research Center. That was in 1996. So I think it's probably coming soon. I'm not quite certain.
Things take a long time in nuclear world.
It does, yes. And the concept of over-engineering and sometimes the emphasis on reactor safety can really push back the deployment, right?
Yes. And did you start to see some of that creep in even with the advanced heavy water reactor?
Safety was always big, in the sense, we would never design anything that is unsafe.
Right.
Yeah. So it was a normal practice at that time in India when things go wrong. We would just shut down the reactor. That is not something which is done here.
Explain that. What is the difference in operation pedagogy in terms of just shutting down the reactor versus not?
So again, I won't be the best persons to talk about this. This is something offhand I heard. So maybe I can't really comment on much more than.
We'll get the next person for that one.
Yeah, the reactor operation. So looking at the capacity factors. Yeah. So in the U.S. we have like 91, 92, and it's climbing over the years.
Yeah.
That's not the same in India, at least when I was there long back. Maybe it's approaching 90, but I don't think it's still there. Now, much earlier on, it was more like 70%. So
yeah. Even here too in the U.S., I think 60% was common back in the 70s and 80s.
Exactly, yeah. And there was the emphasis on shutting down the reactor probably for reasons that may not need a shutdown. Yeah. So it's on that statistical part I'm basing my observation. Yeah.
Okay, so where did you take those learnings at that point? What did you start working on?
So started working on safety codes.
Codes. So this is like computer codes.
Computer codes. Yes.
This is to model how these systems behave.
Yes.
And what part of the system were you modeling?
So I started working on a small part. It was the refueling of CANDU reactors. So unlike in the US or the light water reactors, CANDU reactors can be refueled online. The reactor doesn't have to be shut down for changing the fuel.
And how does the refueling work in a CANDU reactor? What does it look like?
Yeah, so the design is very different. In CANDU reactors, we had pressurized tubes. These are long tubes, and the fuel elements are in the shape of short fuel bundles. So unlike the fuel assemblies that are like 3 meters long here, the CANDU reactors have shorter fuel bundles.
Yeah.
And unlike the fuel assemblies that are vertical in light water reactors, CANDU reactors, the fuel bundles are placed horizontally in pressurized tubes. So it's not a big pressure vessel. There are several small pressure tubes, and these pressure tubes are contained in a big vessel that holds the moderator, which is heavy water. So it is heavy water cooled, heavy water moderated, and the big vessel is called calandria. I don't know how that term came, but it has a nice ring to it, calandria. Yeah, that's a low pressure system. Yeah.
And these tubes, what do they look like that allows for this online refueling? Are they just open on the ends, or do they have doors?
No, they have two huge refueling machines on both ends.
Okay.
So one pushes in, and the other would take in. As the reactor is operational, we can do that refueling.
And how come that doesn't exist in, let's say, a pressurized water reactor? Or any light water reactor, this idea of online refueling. You could imagine that you still have a pressure vessel with water everywhere that it is, but just wherever your fuel assemblies, those are also channels, and you could just go in and out whenever you wanted.
So it's a very conceptual thing, and it dates back to the first designers who propounded that design. So light water reactors, both PWRs and BWRs, it's a giant vessel, and then all the fuel assemblies are put in some place. Now, conceptually, it is a much simpler design because you have a big vessel, you put all the fuel assemblies, and the downside is we have to shut down the reactor to refuel. Now, CANDU, conceptually, it is a little more intricate. it's not one pressure boundary for the whole reactor. So in many ways, it has enhanced safety features. Because you can potentially think of pressure tube rupturing.
Yes.
That wouldn't affect what's happening in the other.
And does that happen in CANDUs? Every now and then you spring a leak?
Not really. Other leaks are there,
Yeah.
but the so-called double guillotine break-in, I don't think it ever has happened in any of the reactors.
And what about within a fuel bundle? Does the fuel bundle ever malfunction inside of a CANDU reactor?
Well, it's the same as the other, in light water reactors too. Now, since they are small, things like flow-induced vibrations and things like that are minimized. They are not as long. And of course, there are supports in light water reactors, but the smaller ones tend to have lesser problems related to flow-induced problems like flow-induced vibrations. Yeah.
How long does your average fuel bundle stay inside of a CANDU style reactor? I know in a PWR they stay in anywhere from 4 to 6 years, let's say. How long does any given bundle stay in for a CANDU?
I don't remember that on top of my head. I would say a couple of years.
Yeah.
Yeah.
And another thing that I've often wondered about these types of systems. So I imagine that like in your fuel pen for your standard light water reactor, as fission gases are produced, they would either and get outside of your pellet but are still inside your pin. I can imagine that they would, depending on the density, go to the top or the bottom of the pin and then get out of the way of neutrons. In a CANDU reactor, it seems to me if you're horizontal, the gas would still just kind of stay, and especially the way they're kind of like stacked within the calandria, you don't get to move your fission gases out of the way. So you're just still bombarding them with neutrons?
Yeah, I mean, there is a big neutron field around the reactor in light water reactors and CANDU. The problems we face in light water reactors are similar to those faced in CANDU reactors too, when it comes to fission gas production and all those things, because they're all nuclear related.
Yeah.
Geometry plays a big role, definitely. I don't know exact problems faced which are unique to CANDU. I didn't work a lot on fuels.
Just early code development?
For the safety, like accident analysis.
Okay. So so what are some of the other scenarios that your codes had to account for in terms of accident analysis?
Yeah, so there was an incident. There are several power plants in India, and Aurora was one of them. And there was an incident that led to shutdown of the reactor, and probably a little bit of core melting, maybe very little, but it was a serious enough accident. And I was one of the younger guys. They didn't have many people to run these big safety codes, and it was on-the-job training for me. We work day and night to really figure out, given the conditions the plant supplied to us, we were trying to model this with a code called RELAP.
RELAP.
Yes.
Which is the thermohydraulics
Thermohydraulics code, yes. And that was my first initiation into that safety code. I didn't work a lot on that side, but that was quite an experience in figuring out, what went wrong, and how could we come up with certain scenarios that could have likely happened in the reactor, during that incident. Yeah, so very informative. Yes.
And when did you come to the U.S.?
So, as I said, I was looking for a research kind of job, and at some point I realized I had to take a master's degree or a PhD to really do research at the highest level. And so I was looking for opportunities both in India and the US. Fortunately, I got a couple of, I got financial assistance and admission from a few universities here. NC State was one of them. I just picked NC State. I came to study plasma flow.
And have you been here ever since?
Yes, ever since.
Amazing, yeah.
Yes, yeah.
And so you studied plasma flow. What specifically?
So my initial thoughts were in fusion reactors. I wanted to, digress into another topic. This wasn't for fusion. So I joined Mohammed's group.
Yes,
met
we
him
interviewed
yesterday.
earlier.
Yes.
Yeah.
So I wanted to do computational fluid or plasma dynamics. So Mohammed had this big grant from, I believe it was Navy. It was for developing an electrothermal gun. So it was like a laser ablated plasma that would thrust a projectile to
A
really
launch
high.
mechanism.
Yes.
Yeah. So you were working on that project.
From a computational point of view. And
Yeah.
Mohammed had experimental facilities to test that. And the projectile would go to amazing speeds, like 7 kilometers per second.
Get at it. That's like almost escape velocity.
Yes, that was the idea.
That's incredible.
Incredible, yes. In fact, the Navy wanted to go as high as 10 kilometers per second.
Wow.
Yes. You can shoot projectiles to space.
So that was part of the concept.
I guess.
And would that be a weapon system of some sort?
Yeah.
So almost like a ballistic missile launched from here to space, drops back down, looks like an asteroid, blows something up.
Yeah, well, those hypersonic velocities were, I'm sure there are reasons for navies,
Yeah. They like to blow stuff up. That's the reasons.
Now, they did deploy these electrothermal guns in ships.
Yeah.
So 15 years, 20 years later, I saw a YouTube video where they actually...
wow, for railguns.
Yes.
Wow.
And so there are no ammunitions, We just have this projectile thrusted to this really high speed. So the energy that is coming is from the kinetic energy of this projectile.
Wow.
Yeah.
So when did you shift your focus back to outside of the plasma space and back
to nuclear?
Yeah.
So I was planning to do my PhD here. At that time, 98, it was a low point for nuclear.
Yeah, I've heard.
Yes, and there were a few jobs out there, Arriva and Westinghouse. So I took a job, to see, really experience the U.S. nuclear industry.
Yeah.
So I went from here to Lynchburg.
Yeah, for Framatome.
Framatome.
Yeah,
Yes,
so
yes.
Arriva, I guess, was called at the time.
It was Framatome, yes.
And what was that experience like for you? How was it different than the academic world? What did you learn? How did you see things differently?
Yeah, so very different from academic world, and we cater to customers. So different plants have different problems. Accident analysis was one of them. There were other problems related to safety, thermohydraulics, fluid flow, heat transfer. So I worked on many little projects. These projects would last like 4 weeks, maybe 6 weeks. Very interesting, small projects, but I learned quite a bit on the actual workings of the industry.
Yeah.
Yes.
And but you decided you wanted to get back to academia.
Yes. In 2 years' time, I thought, okay, probably research, and master's is not enough. I need to take a PhD. So,
yes.
Yeah.
And where did you get your PhD?
So I went to MIT. And my first instinct was to go into thermohydraulics area. Then I was talking around and I learned about the fascinating world of material science. And having worked in the simulation field, the computational aspects, the modeling area for so long, I had this natural inclination to do computational material science. And I was very fortunate to work with Professor Sidney Yip. He's a very well-known computational material science person. He does a lot of stuff, including nuclear materials, but he also worked on other materials and systems. That was quite an experience.
And what makes computational material science different than just testing and experimenting with materials?
Yeah.
What's a fundamental different approach there?
Right. So, we can think in this way. In the good old days, there were kind of two pillars of science. One is experimental, and the other one was theory. Theory is more recent, but most of the science, the underpinning of science is experimental. Now, late 19th century, we started having the theoretical emphasis. Maxwell's equations came in, so, and of course the big explosion in relativity, the quantum mechanics. So theory became a pillar of science.
Yeah.
Now, after computers were invented, the first ones actually came out of Los Alamos, right? A new branch kind of slowly evolved, which is a mix between theory and simulations. We take theory, the concepts, but we do experiments on the computer. So that became almost like an entirely different way of inquiry. And nowadays, we tend to think computational science as a third pillar of science.
And what are some things that we've learned, whether in your lab or just in the broader picture, what are some things that we've learned just from computational understanding materials that we couldn't have learned from theoretical or applied or experimental?
Plenty of things. I might bore you with some
Bore me,
details.
go on. None of it's boring. It's nuclear. It's all exciting.
So one of the things I worked here at NC State was on graphite, and graphite, it's a particular allotrope of carbon. The more famous one is diamond, very expensive.
And that just describes the geometry of how the
crystal structure.
Crystal structure.
Yes. So how atoms are placed in a lattice.
Yes.
So graphite is very interesting. It has a planar structure, meaning on the planes, the carbon atoms are arranged in a honeycomb type lattice, and they are very strongly bonded on a plane. Now, there are many, many layers of that kind of planes, and they are loosely tied to each other. So these layers can slip or shear very easily.
And that's why when you draw with a pencil, little layers slip off onto your paper.
Exactly, yes. So that's a mix of clay and graphite. So I believe the B marker of the HB pencils.
Yeah.
The B refers to how much graphite it has.
Oh, I didn't know that. Interesting.
I think that's the way it is. Yeah. So graphite was the first moderator used by Fermi in his Chicago pile. Yes. So that is also used that was also used by the British in England. They had these high temperature gas reactors, cooled by gas and moderated by graphite. So that is a well-known, well-established program. Now in the US, we started that program long back, 1950s. I think the aircraft reactor program was there. That didn't quite pan out well. In the 60s, Oak Ridge took initiative, and they built a molten salt reactor with graphite moderator, with a graphite moderator. It ran for a few years' time, then it was shut down. Now, currently, DOE is investing, looking at possibilities of next generation reactors that can go to higher temperatures. Now, why higher temperatures? It is thermodynamic efficiency, right?
Right, because it's that delta between your high temperature and your low temperature.
That would, yes, that's the ideal Carnot cycle. The efficiency, right?
Yes.
So we would get more heat or work done if you can go to higher temperatures. So there is this there is a good rationale to build reactors that can operate at high temperatures. So, and graphite is a great moderator. It can withstand high temperatures.
When you machine graphite or make graphite, what actually allows it to stick together? Like, is there a bonding agent as well, or is it really just pure graphite and just kind of just slapped in like, how does it stay in its form and not just fall apart?
It's done through the processing technique. Once it is graphite, no, there are defects, there are grain boundaries, and localized regions that are kind of amorphized and all. But all in all, overall, it will retain a crystal structure, and it can withstand these high temperatures, neutronium radiation, and so forth. There are obviously, the microstructure changes with neutronium radiation. For example, in graphite, the big voids come in, and it would creep and things like that.
Where do these voids come from?
The fission gases. Yes.
Right.
So yes. Yeah. So
okay.
Yeah. So those kind of things can happen. And one of the first projects I had was on creep of graphite, and I worked with my colleague here, Dr. Murthy. He's a great friend of mine and a mentor to me. He and I worked on many projects at NC State. I would do the simulation side. He's a very well-known experimentalist. So we had this great. It is still continuing, and so we had worked on many projects together. And the graphite was one of the first projects we worked on.
And so what did you discover there? Yeah.
So back to your question,
yes.
What did we discover from simulation that couldn't be seen from experiments, right? So one of the things we looked at was how the defects are formed. So the conventional wisdom is that you would get lots and lots of defects between the layers because they are weakly bonded. And you would think that there may not be as many defects as the interlayer defects on the plane itself. Now, with simulations, we were actually able to show that we could get lots and lots of different types of defects that are ring-like on the layers themselves. We call them as topological defects because the connectivity, topology is related to the connectivity of the bonds. Really hard to get information of that kind of defects from materials characterization.
And because it's so small.
It's small, and we can get a good idea provided we look for it.
And what is the effect of the defects on the overall structure?
So defects would lead to deterioration in mechanical properties. It can become more hard. It can creep more. The dimension itself would change. That we don't want. We want to keep it within tolerance. So the defects affect the material in material's properties, dimensions, dimensional changes.
I see. Yeah. And the measurements that you're taking, are you simulating neutron bombardment of this material?
We do, yes.
I see.
Yes.
And what isn't the behavior of most materials that they'll swell under radiation, but graphite will shrink under? Is that true?
So
more nuanced than that?
The graphite is an interesting material. It does both. In one axis, it shrinks. On the other one, it expands. So it has this peculiar behavior under radiation.
But which is important to know if it's part of your structure.
Yes, definitely. Yeah.
Very cool.
So all those things are known, since the 80s, since the 60s. We have a good idea. Now, things like these topological defects were not even known. Well, it was loosely known, but how prevalent were there was not known before. So through our simulations, we were able to show, we have substantial number of these defects comparable to the interlayer defects, which were more prominent. Yeah. So that was one thing, we could show from simulations.
Yes. What other type of work does your lab focus on?
So I have worked on back to the high temperature reactors. So when I joined NC State 2008, I was looking for material science projects because I did computational material science in my PhD. And following that, I went to Los Alamos. I worked with Art Warder briefly for 1 year. He's a well-known scientist in the area of the so-called accelerated molecular dynamics, where you can access more time in an atomistic simulation. I didn't spend enough time with him. It was just a few months, less than a year. But I came to NC State and I was looking for materials-related projects. So graphite was one of them. Another project, me and Steve, we worked together, was on high temperature properties of UO2, the fuel.
Yeah.
So now fuel properties are, again, you would think it is well known, but not necessarily on the high temperature side. We are talking about temperatures greater than 2000 degrees centigrade.
Wow. Could you operate fuel pellets at that temperature?
We don't typically, but during accident conditions, it can.
Yes. What is the centerline temperature of a UO2 fuel pellet in your standard reactor?
Again, I don't remember on the top of my head. It could be around 1500.
Yes.
Yeah.
Okay.
It is less than 2000 degrees.
But we want to know what would happen if it got up to 2000 plus.
Exactly.
And it's a ceramic. So how hot does it get before? How does a ceramic behave at those high temperatures? Does it crumble? Does it melt? What does it do?
Very interesting question. And that was what we started working on. Okay. So UO2 has a peculiar property called superionic property.
Super
ionic property.
Okay.
So that is increasingly being investigated for battery materials. So this is how it works. Beyond a certain temperature, if you have two species of atoms, so UO2, we have two species, uranium and oxygen. Beyond a certain temperature, the ions, one of the ions would start diffusing like a liquid. So it is solid state. The uranium is keeping the whole lattice in place, but the oxygen ions are diffusing in and around these uranium pillars.
Wow.
So it's yeah.
So the uraniums, they're holding on to each other.
Yes.
And then they
and
also
providing
hold on
the backbone.
to oxygens as well.
No, the oxygens,
and the oxygens start flowing at the high
flowing
temperatures.
at these high temperatures.
And then, but then doesn't it become metallic uranium at some point if the oxygens flow away?
No, it's kind of liquid oxygens.
Okay.
Yeah.
So it's kind of in an odd phase.
It's an odd phase. We don't even know whether thermodynamically it can be even called a phase. And those are some of the things we investigated. And
is it possible to simulate this behavior on other materials at lower temperatures that might express
definitely
this? Okay.
And people have done that in the past. And by the time when we started looking at it, we were able to simulate this behavior in UO2.
Wow.
We were able, so there were a lot of, I would say, conflicting theories on what happens at high temperatures. And this is where simulations are definitely a big help. So the way we understand crystal structure is through a technique called diffraction. So diffraction can be done by neutrons, can be done by X-rays. Now there is another technique called scattering technique. It can be again done by neutrons, X-rays, and so forth. We would extract information on not only the positions of the atoms, but also on the dynamics.
Is it while it's in this state,
yes,
while it's in this high temperature state, you're able to image it?
It is not imaging, it is a spectroscopy device or a technique.
Okay.
We would get data. Now, we would get data about something called dynamic structure function, okay? Very abstract. Now, we have to make models to make sense out of this data. So the data is good, it is the truth, if you want to call it that way. But what we infer from that is not necessarily the truth.
There's layers of abstraction. Yeah.
Yes. So what happened was in the early 80s, England, UK, they were the leaders in neutron scattering techniques. They mapped out this behavior. Well, they predicted that the oxygens were leaving the lattice, and the evidence was good. It was excellent, but they couldn't fit these motion or the movement or the placement of the ions into any known models. So they came up with things like dynamic Frankel pair model and all those things. But there was one person, even back then, 80s, he was a molecular dynamics simulation person. He said, no, the ions are just jumping from one lattice to another. Forget about this Frankel pair and all those things. You're trying to fit things into a model which is not working very well. It is much simpler to think that as you raise the temperature, the ions would just jump from one place to another.
The ions are jumping.
The oxygen ions are just jumping.
But is the oxygen itself jumping, or just the electrons, or
the whole atom?
The whole atom is
yes.
Okay, got it.
Yeah.
They're jumping from one place to another. So not flowing, but jumping.
Not flowing, but jumping, and they are not displaced as defects, but they are just jumping.
Okay.
Yeah. So, and that was a kind of controversy at that time. But then, in the intermediate period between 80s and early 2000s, we didn't have a lot of research work going on in this direction. So that was the kind of end of story. And then I picked this work up. We saw the same, like the ions were jumping. Not only we did that, we matched this disorder to neutron scattering data. They lined up perfectly well.
Wow.
And not only that, we were able to go to another physics world, the world of supercooled liquids, where atoms are in a frustrated state. When you cool things very fast, atoms are in a dynamically frustrated state. And what happens there is the atoms tend to follow each other along a line. It's like in a big crowd. and you want to move. You would see one person moves,
Yes,
but then
yes.
he's usually
Oh,
alive.
that's an amazing analogy.
Yes. And we found exactly like that. We found string-like motion. We
So almost like
quantified
little
that.
rivers
Little
of
rivers,
oxygen flowing.
And
And
that
where do they
was,
flow to at the end of the day? Do any of them pop out the edge, or
well,
they just find some circle and keep going?
circles and keep going in an equilibrium
Kind of
state.
like a conga line.
Yes, yeah. Now, if you put in a gradient, it would go from one gradient, one place to another if you apply an external gradient.
Yes.
Yes, but if you don't do that, we actually see this going, in little rivers as you described.
And what happens when you cool back down again? Do things lock back into place?
Yes.
Okay.
Yeah. So these are some of the things, and my student and I, Ajay, he published around 7 papers on this, the high temperature properties of UO2.
And then what happens when you go even higher?
Higher,
At what
okay.
point does the structure totally decompose?
Okay, so then it goes to some pseudo phase transition called Bredig transition or lambda transition. That's also well understood. Very difficult to measure that in UO2 because of the high temperatures. So around 2700 centigrade, I believe. Yes, the specific heat, it shows an anomaly. It kind of shoots up, and then it comes back. So if you draw it, you will see this, unnatural behavior in the specific heat. Other properties remain fine, like thermoconductivity and all remain fine across interval. So physicists understand this as a so-called second order phase transition.
Because you're able to absorb more heat without changing phases? Is that what?
So the terminology...
Or is that the temperature increasing, I should say?
With temperature increase, yeah. So there is no real phase change at that particular transition. It's more defined in terms of slopes and whether there's a jump in the slopes and things like that. It's kind of abstract, but people tend to think this as a second order phase transition. Now, it's everyone. It's not well established, but that's a good way to look at it. So we were able to predict that too. And fortunately for us, people before had developed good interatomic potentials that could actually predict these anomalous behavior. After that, so that was the so-called superionic transition. It was only after that 2700. Let me just say, I think I may have confused centigrade and Kelvin. All these were Kelvin. Sorry. So whenever I said centigrade, yes, well, plus 273.
Right.
Yes.
At least it doesn't scale differently.
Right. So after 2700 Kelvin, that was the original transition for superionic transition, where the oxygen ions become completely liquid-like. What we were able to show was that as early as 2000 Kelvin, the ion starts moving from the lattice. It was slowly developing. It was not like a transition as such.
Yes.
There is a broad spectrum of temperature over which
I see. So at the lower temperatures, the oxygens are moving more like little rivers. And then as you get higher temperatures, it's more of like a pond in general.
You're right. So at low temperatures, you have small number of very long strings.
Yes.
As temperature increases, you have more of these strings, but of shorter nature.
Yes. Now let me ask. During this, at these temperatures, if there are fission products that are trapped within your UO2 pellet, just kind of scattered in the middle there, do they also flow along these rivers? Are they able to move more readily in this state?
Yeah. So that's the question. We are looking at it right now.
Oh, okay, great. Because
Yes.
you can
And
almost
that is
imagine
the implication.
You could almost imagine
Yes.
purposefully raising the pellet temperatures in almost like an annealing fashion in order to evacuate out the fission gases which are causing the swelling and property distortion. And then when you evacuate all those fission products out, when it returns back to its state, it's a more stable structure.
Okay, I didn't think about that as an engineering mechanism.
As an
right?
engineering mechanism, it's almost like you go through, like with your oven. You ever do a cleaning function in your oven, and you just crank up the temperature for a while, and it's clean somehow.
Yeah.
Maybe you could do that with the UO2 pellets to clean them of the fission products.
So yes and no, I guess, because many of the fission products do not take the place of oxygens. They take the place of uraniums, and uraniums are kind of, they are the pillars. They stay there until melting.
Yes. But you could imagine if there's stuff flowing and oxygen, yes, as long as the fission products were small enough, perhaps they could creep by with the oxygen.
So that's the thing which we want to look at it a little more carefully. Now,
And what is the bond? What is that? Do we have a measurement of the strength of that bond between the uraniums?
So UO2 is mostly an ionic material, but it has certain covalency also. So there are ways to describe that interaction quite accurately. So we are able to get all this, this lambda transitions and even the specific heat values, absolute values. So there are models by which we can get to those numbers quite accurately.
And what point does it break? What point do we start breaking do we have a temperature that we start breaking the uranium
that's the
bonds?
melting point.
That's the melting
yes.
point. So what is the melting point of UO2?
3,200.
Pretty high.
Yes. So there is a window between 2,700 to 3,100 or 3,200. The oxygens are flowing.
Yes.
And that's the property we call as the superionic property.
Superionic.
And that's what we would use in a battery, in a solid state, in a superionic battery. This is what we take advantage of.
And so
like lithium.
How does it work in a battery?
In the same way, the holy grail is to have this kind of behavior at low temperatures.
Yes.
So in uranium, we have to go all the way up to 2,000 Kelvin and upwards.
And what does that mean, though, in terms of holding your electric potential? What does the superionic property do for carrying electricity?
So these are ions. So these are charges. So that's current.
I see.
Yeah.
So when you're in that superionic phase, current is being delivered.
Yes.
Yes. Fascinating.
And tons of, there are lots of places, people investigate the superionic behavior, nature of materials for battery applications, thermal storage, and there are tons of other applications too, rectifiers and things like that, thermal rectifiers, and so it's a very interesting field. I myself, because of my background in heat transfer and thermal hydraulics, I was quite fascinated by this behavior. And we also looked at the thermal conductivity of graphite, again from an atomistic viewpoint. Another student, he looked at the so-called phonon transport in non-metallic or insulators. So there are vibrations in a crystal, and these vibrations transfer energy, and that's how some of these, that's how heat can be transferred in a non-metallic material like UO2. So most of the heat that is transferred in UO2 is through lattice waves.
And is that the same as conduction, or is this
conduction?
A different form?
Yes.
Okay, so that is like the official physics definition of conduction.
Yes.
It's vibration.
It's vibrational energy, the transfer of vibrational energy. And what we did was we took look. There are many levels of addressing this problem. There are many ways to look at this problem, theoretically. And one of the ways is through something called Boltzmann transport equation, and that's by far, that's like the standard method. We looked at it in a different way. We looked at it from an atomistic viewpoint. We actually would simulate the atoms and look for waves.
Wow.
And there were...
How do you stimulate the atoms?
The same in a way we were doing UO2 and everything else. So we will place an atom in a certain location.
Yeah.
We'll place another atom at another known position.
Yes.
We know how the atoms interact, the forces.
Yes.
And on a computer we say, the atom number 1 is at place 1, atom number 2 is another place.
Okay.
They interact with this kind of force.
Wow.
And then we do a do loop or a for loop for all the atoms.
And there's no quantum effects that we're not counting for?
There are. The bonding is primarily quantum, and I do a little bit of that, but I am more interested in the collective nature of atoms.
Yes.
Really interesting. As an engineer, I want to know.
Right.
Yes, but there are material scientists who are more interested in the prediction of structures and prediction of new structures. They do quantum mechanics directly.
Yes.
Not the Schrödinger equation. They don't solve the full Schrödinger equation for all the electrons. We make approximations, and there are very good approximations like density functional theory. And I do sometimes, I have an ongoing project where we do this. It's really expensive to do those calculations. So that is one limitation, but
just computational
expense.
Yes.
I do more atoms, and we do millions of atoms at one time.
And it's easier in their aggregate behavior to predict what's going to happen.
So we don't. We try to find something called interatomic potential that would mimic the electronic behavior.
Interatomic potential.
Yes.
Okay.
Which means we can calculate forces between two atoms. That's all we need.
Yes.
Yes. Now, whether that's a good approach or not would depend on the predictive nature of the simulation. High temperature behavior, quantum effects are smaller, so we can get away with these.
Why would that be? That the quantum effects would be smaller at higher temperatures?
So the quantum effects can be quantified by this factor h, which is Planck constant, and a representative frequency of an atom, h nu. We call, that's the energy term. Okay. Now, if that is comparable to the thermal energy, or let us say much higher than the thermal energy, and the thermal energy is defined by, again, two factors, Kb. Kb is Boltzmann constant, and T is the temperature in Kelvin.
I see. So if the temperature is higher, its relative proportion is much smaller.
Yes. So at high temperatures, KBT dominates.
Yes.
H nu is small. Then we get away with that. At low temperatures, the opposite. We have to go to quantum mechanics to simulate things properly.
Got it.
Yes.
Cool. What you guys work with other types of fuels as well? Do you guys try to predict advanced fuels?
Yes. So I have one project which is ending soon on accident tolerant fuel.
Okay. We've spoken to Lightbridge, and
yes.
I think Westinghouse also works with accident tolerant fuel. What's the difference? What is accident tolerant fuel?
So it all started from Fukushima, 2011,
yes.
And 2012 DOE reorganized the fuel program to include ATF programs. So it was more of a laboratory initiative in the first phase, but then 2014, 15 and onwards, a lot of university folks have started working on this. So one main thing is how to control the hydrogen. So hydrogen was the big problem with zirconium, right?
Right. So what happens at higher temperatures, let's say 1100 degrees Celsius, the oxygen in your H2O will want to jump to the zirconium. The zirconium will oxidize, it'll reach out, grab the oxygen, and then the hydrogens will be released. Is that what's happening? The
chemical reaction's happening, and it's exothermic, so a lot of heat is actually produced.
Yes.
And that is the downside of zirconium, or zircaloy, which is the clad material. Zircaloy has interesting properties. It does not absorb neutrons like steels. So that's why we don't put steels in a reactor cladding material.
Yes.
Fast reactors would, but not light water reactors or thermal reactors. We don't do that. Now the quest is to find a good material for the cladding.
What are our options? Do we have other options?
Silicon carbide composites is one of them that is being looked at.
And silicon and carbon are both less visible to neutrons, just like zirconium is?
The cross sections are small, so that is good. Silicon carbide is a composite. It does not chemically react with water as it would react with zircaloy. So that's a big plus. There are problems associated, with everything, and yes, it's the nature
Welcome
of
to the world of materials.
Right, it's the nature of silicon carbide.
Yeah.
It is brittle.
Yeah.
So
not very good structural properties.
Right,
Yeah.
exactly. So that's where composites come in.
Yeah.
So you weave long filaments of silicon carbide.
Almost like carbon fibers, but
for silicon carbide.
For silicon carbide.
Put it
cladding,
in,
yeah.
yes, put it in a matrix of silicon carbide, and you get a silicon carbide composite.
And would this be the entirety of the cladding with this material, or would it also be some zirconium?
No, replace completely.
Okay,
Yeah. And then it's because of its composites, you have to weave it into. It's like weaving, really. Into a functional form like cylinders and things like that. And GA, Westinghouse, Arriva, a lot of people are looking into this. This is one of the ATF concepts for the cladding. There are other ATF concepts for the fuel.
What's your favorite?
A bunch of, not really. A bunch of concepts out there. Nitride fuels. So in nuclear, many of the concepts we hear now have been tried out in the 60s.
That's the world of nuclear.
It's right. Things we speak now, there is a good chance that someone in the 60s did that in Oak Ridge or Los Alamos.
Amazing the freedom that they must have been afforded to just try literally everything.
It's amazing. That period of time, I don't think we can recreate.
Why not?
Yes.
Why not? Since we have to wrap up anyway, let's end up on this note. I want to hear your thoughts as to where we can go in the future and why we can't have a world that was like 1960s Oak Ridge and Idaho National Labs, Argonne West.
It's money, and the money was provided by military. So there was this huge, tremendous interest by Navy to develop nuclear reactors for their submarines and aircraft carriers.
But doesn't I heard some ridiculous number like the military spends as much money on energy as like the 6th largest world economy would, or something crazy like that.
Right.
Isn't there still a lot of money from the military for energy?
So the need is not there. Their submarines are working very well. The aircraft carriers are working very well. At that time, there was a need to replace the noisy diesel generators that could be easily detected by the Russians, Soviet Union. Now, it's that kind of need is not there, and so the Navy is not going to spend, and all kinds of concepts were being tried out. Air Force, like I said, the molten salt reactors. That was the first one was supported by the Air Force. These days, they're not that keen. So that's a different era. I find it very difficult to think that era would be replicated again. Okay, so I'm going to make you end on an optimistic note this time. Paint the happiest case scenario for where the nuclear world goes 10, 15 years from today. Happiest, so personally, I think climate change is real, and the fossil fuels are adding a lot of carbon into the atmosphere and to oceans and so forth. And to counter that, we need a carbon neutral source like nuclear to reverse the effects. And we talked about that a lot, and I'm looking forward to your seminar today, how to reverse that. And in my mind, in your mind, and in many people's mind, nuclear is the way to go. We cannot scale other renewable sources, at least with the present technology, like with batteries and things like that, to the level nuclear can go. So I'm really optimistic about nuclear, and my wish is this: we will find the next generation of people with the next generation of reactors that can scale up to what we had in the 60s. That may not be the big reactors we see now. They could be smaller reactors. They could be, as you suggested, could be swimming pool type reactors. But I hope the new generation would take this challenge, and I also hope they see the bright side, and the need for nuclear. Jacob Eapen, thank you so much for everything. This has been a blast. We could keep this going forever, but we gotta go. We have to be continued. To be continued. Thank you very much. Yeah.